Okay, welcome back to the 424 School of Engineering, everyone. Today we are gonna talk about tires, suspension, and brakes. I believe it's module number 6, and we'll have one or two left after that. And before we start, I will, as always, talk to you a little bit more about Perrin and the team and the latest development. And there is something that I have been working on that I want to show you. So I call this the big plan, and the idea is to just explain a little bit what Perrin needs to become and how we're going to get there. So very quickly, I want you to understand that Perrin is more than just developing 424 and the electric hypercar project. Really, the vision behind Perrin is eventually we need to become an innovation network, but with team values at its core. Obviously, you've always heard me talking about we are a team and we are building a team here and a platform. What we are doing is innovation. We're solving problems. We're creating new ideas. We're building new products and projects to improve and leave, have a positive impact and a global impact, whatever project we're working on. So as I put it here, Perrin is a place where people and companies will access valuable information, investment opportunities, and we also want to develop open source technology. It will not always be open source. Some of it will be closed source, depending on the nature of the project. But as much as we can, we want to develop open source technology. And remember, we're all members of an open and a democratic network with common goals and shared benefits. And this is really the team values and the spirit behind the way we're going to develop this network. As I said, we're really working on what I call high impact products. So something that can leave a positive change, includes open source technology, and also have a sustainability associated with it. So the product that we are working on right now, and actually this is fairly new, the token, and I'm going to explain to you what this is. It's not new in the concept, but the branding PRN token is new. Obviously, as you know, we've been developing 424 for a while, so this is our main product, and this is why you're here today and why our community has been growing. So obviously 424 is divided in two projects, as you know, the 424 Nürburgring lap record with the battery version of the car before going to Le Mans 24 hours in the future with a hydrogen version of the car. But let me talk quickly about the PRN token. As I've already mentioned, and some of you will know, we've been doing crowdfunding, and for a while now, we've been raising some money from from our community. And the way we've been doing it was we have this contribute button on perrin.com up to this point. So we called it a contribution into the project. But what I want to go towards more now is what we call tokenization. So effectively, we are going to transfer everything that's been done up to now. It's going to go on the PRN token. So our 85 contributors up to this point, myself included, we have credit in Perrin. And in fact, today we had a new member purchasing some credits in Perrin. And that will transfer naturally into the PRN token. So what people will see as the value they can invest in is the purchase of the token. At this stage, everything we do is kept on a database, traditional database. But the idea of the token is that eventually it will become a crypto token on a blockchain technology, which is the best place to effectively tokenize projects or assets. And there's lots of other companies starting to do that. It's fairly new concept, but it's recognized as the best way to democratize ownership of assets or companies, right? So this is how Perrin is going to become owned by a big crowd. So the PRN token, we've launched it this week as a branding, as a new branding, and there's work to be done now to integrate it into the Perrin.com platform and replace the older system that we have with the PRN token. And as I said, it's a seamless transition between what we've been doing with our contributors up to this point and going towards talking more about token holders. And I hope many of you will start seeing the value of holding the token and wanting to purchase token. So the stage we're at now with the token, I will explain in a minute. Just to give you an idea that in the future, once our network is up and running, these are just examples of things we could develop with the Perrin Innovation Network. Okay, as long as we're working on sustainable, open source projects that can have a positive impact, then we might get involved and invest into these new projects. But for now, we're going to remain focused on 424 and the PRN token to raise capital for the projects. Quickly, I want to reiterate the values that underpin our network. And this is what I call the team values. So effectively, we want to be a very trusted network. Everything we do is open and transparent, and this is the best way to build trust for people who are watching us from the outside and starting to be coming into the community. So the Perrin.com is the best place to see in real time what is happening inside the network. We are a team. I keep saying that this is our motto. And for me, it means effectively being a high performance team, being accountable for what we are doing, having integrity, teamwork and collaboration, innovation, problem solving, and working together to find solutions to problems, building trust, as I said, openness. It's about letting people coming from any background coming into the team and having the easiest way possible for people to come into the team. We have passion and we want to work on exciting projects, and diversity. And as I said, we want people from everywhere in the world to be able to integrate our team. Shared ownership, that comes from the PRN token I've just talked about. It's very important for me that you understand with crypto, we are transitioning from a world where effectively wealth and valuable investment was only accessible by a handful of people. And effectively the rich people are getting richer because they are the only people who can access valuable investments. We are transitioning to a world now with crypto where this will become accessible by anyone, by you, me, everyone can effectively easily invest into valuable projects and network like Perrin. And as I said, we want to work on projects that drive positive change. Just a bit more about the PRN token. So where we're at now is we are doing what we call effectively the pre-sale. So we are allowing anyone to purchase tokens from the network, and that is happening on Perrin.com. And we will market that and talk about this more and more on LinkedIn and social media platforms, just to make people understand that at this stage we are raising capital. That will allow us to then put the token on crypto blockchain, and that needs some energy spent to allow that transition to happen. And at some point, people will be able to start exchanging their tokens with new members and effectively realizing returns and on their investments. And what we want eventually to have is a full integration in pairing.com, talking with the exchanges and having this very seamless way of purchasing, exchanging, and selling tokens. Okay. And the last thing I want to say is that because of the team values that we have for the network, if you think of the price of the token, so obviously traditionally, price of shares in companies or assets is fluctuating a lot. The blue trace here is the Apple stock price for the last 30 years. And this is a logarithmic scale, by the way, because these companies and these projects tend to have an exponential growth. So it's easier to visualize them on a logarithmic scale. The yellow one is Bitcoin, and we know it's going through very high, very fast, ups and upside, downside, and price fluctuation. But really, what's happening here is people are betting against each other, and it's a marketplace where you want to try and buy the asset when the price is low, sell it when the price is high, but effectively you are doing it on your own, and you're trying to sell the assets maybe to your friends when he wants to buy, and you think that actually the price is too high and it's the right time to sell. That's okay to make a marketplace work, but it doesn't really fulfill the values of the team for me, because in this situation, as an individual, we are betting against the others and we are fighting against each other in these markets. So the idea of the pairing token is that we are going to actually try and control the growth of the price at a certain level, which will match more or less what happens with tech stocks like Apple, which are growing at about 20% per year. But we will effectively have a way to limit the fluctuations by issuing new tokens when the price is getting higher than what we are targeting. For motorsport engineers, it's like having a traction control. Effectively, it's limiting the slip of your tires by limiting the power. So we'll do something similar with price, just trying to make sure we're all following the same growth and we're into this together. So it's quite unique in the way we're gonna raise capital and allow people to invest in a very safe and predictable environment. Okay, so I will stop here when talking about this, and I'll go to the School of Engineering now. But if you have any question about what I've just talked about, please don't hesitate to raise your hand now or question on the chat. Yes, Wojciech, we have a question. No?
Forgot to unmute. Hello. When someone contributes to the project rather with work or expertise, is it also transferable to tokens in some way?
Correct. Yes, it is. We have done that for a while, and we will keep doing this. So if I go quickly on pairing.com, what you're finding here is that we have a directory of all the people who own tokens. As I said, the user interface is going to change soon, and you will see PRN appearing, and also a price for PRN and an equivalent value that people hold, which will be what you see here. If I take some examples, for example, Eddie, in fact, David as well. David, who owns quite a lot of tokens now, he was by my side for 3 or 4 years and found actually Eddie and another company and did a lot of the groundwork with me. So he invested his time for a long period of time when we were more or less the two of us at the time. Eddie then came on and has invested a lot of time in building the Unity simulation that I have presented a number of times, and is still working on it. And you can see him interacting on pairing.com when he's investing time and building the features that we need. The same for Ian. Cameron came actually and invested into the CFD process 2 years ago, so he put some money up front, plus he has invested time as well. Alex has invested a lot of time and money as well into the process. All of this is open. I can talk about it because all the data is on pairing.com. So most of the people you see here have invested a lot of time. Augusto has invested time driving the car.
How do you evaluate this work, this time?
Yeah. So the way it works is every time somebody spends time, well, I've done it today. You see the message I posted with 3 superior is basically 1 hour for each, so it's 3 hours spent. And you will find that we have our driver here, Damien. He was driving for 2 hours.
So it's just hour, right?
It's hours, and every hour is converted into value based on a contract that you can sign. The contract is coming from your settings on pairing.com. If I go in my settings and I'll show that to you, you can do the same. The pairing contract is here. So you can log in on pairing and fill in this form. And there is a level from 1 to 10 that corresponds to your level of experience. And 10 is the maximum, it's expert level. And that combined with the hours you spend is basically giving you some tokens automatically. Now, that's how it works. And that's how we've been working for the last 4 or 5 years with all the people that have got tokens. And that's why we've been able to develop Unity, done a lot of social media work, and etc. etc. So anybody can participate this way. But I just want to say that we need to have a specific task that we agree beforehand, obviously. And the work needs to be valuable in the sense that it needs to be something that we need for 424, and then we start working together this way. But it's worked with, I can imagine, about 25 or 30 people have contributed this way.
Thank you.
Okay. Any other question on this topic? Okay, I'll switch. Maybe there's another question. Yes, Lauren.
Thank you. With the investment, I do remember asking you last week about it as well. This is a slightly different question though. Looking at the time frame that you have, like certain levels, are there levels for financial investments as well, or is that calculated differently?
So I'm not sure if I understand completely the question. So you're asking for financial investments. Basically, we are all on the same. It's all the same terms for everyone.
Okay.
There's basically a price for the token, which is more or less €1, $1. That will be updated on pairing.com to be more clear. And the price is going to go up automatically at the moment 10% per year, but it will increase a bit faster soon.
Yeah.
And you can basically purchase tokens at the current price from pairing.com. And this is how we are raising capital. And we're going to explain exactly where the capital goes and what we're doing with that money in order to grow the network.
Okay, brilliant. Thank you, Nico.
Thank you, Lauren, for your question. Okay. So I will now move on to the topic of the day. Okay. So let's talk about tire suspension and brakes. As the same as last time, this module might be a little bit shorter than the 2 hours. We'll see. I want to give you more details on these 3 separate topics. The tires we talked already about a little bit, but I want to come back on that topic a little bit. Suspension, I will explain more on the design decisions and the parameters we're using. And then I'll show you what brake system, how it works for 424. So let's start with tires. And I have effectively gone through this before with some of you, but we have this document, the tire model, and I'll go into it in a second. And these are like the main parameters for the tires that we've selected for the car. And I'll explain why we've selected these tires and how we've done it. And then we mirror all these parameters into our tire model in Unity for our driving experience and our dynamic testing. And this tire model on the right-hand side is the tire model that is completely designed and built by Perrin. So effectively, we've agreed on the tire model, and Eddie has been integrating this model into the Unity simulation. The reason we wanted to build our own tire model is to be completely independent from needing at this stage to get models from a tire manufacturer, that there is all sorts of confidentiality, and until we are going to the physical stage of 424, it's easier to build our own model and get that model validated by people who have access to the data. And that's what we've done. So if I open this document quickly, so what I did was I took the dimensions from the regulation from the Le Mans hypercar regulation, which I summarize here. There are various dimensions for the front and rear tires at Le Mans, and it's basically all the tires use 18-inch rims. So this is like a box where the tires needs to fit inside that box, and it mirrors the section that I've put on the left-hand side. So the rim dimension is always an 18-inch rim, which is the dimension that Formula One is using now. Before, they used to have smaller rims, and they've gone to 18 inches. And the maximum diameter is always 28 inches. I've put these numbers here, and in centimeters, it's 71 for the diameter, and the rim, and the width we are using at the moment is 14 inches. So the width, we have 3 different options for Le Mans 24 hours, 13.5, 14, and 15. And depending on the category you're racing in, there is basically, you can go with the smaller tire, and it will give you access to a different level of hybrid boost, if you like, or you go to the bigger tire and you've got less hybrid, or there is a different speed at which you start using the hybrid. I'm talking about Le Mans regulations here, which doesn't really apply for 424. But the reason I wanted to mirror the dimensions is because when we go and buy a tire, I need to make sure that this tire is available, or the tire is built inside a mold, and you cannot really do a specific dimension for yourself. The cost would be really high to change that. So it was important for me to estimate what tire we would use, what tire dimension we would use. So we have effectively the 14-inch width front and rear, same tire. Having said that, it's likely that we will, when we go to the physical car and we select the final tire, it's likely that we will change some dimensions around. The rear is going to be a bigger diameter. The reason for that is we've basically talked with some people, and because of the vertical loads being higher on 424 than the Le Mans cars, we've got more downforce, and we go to 360 kilometers an hour. At Le Mans, they go to the similar top speed or slightly lower, but there's much less downforce on the car. So using a higher diameter tire will allow us to not have to increase the pressures too much. We're already going to use about 2.3 or 2.4 bar, which is already higher than what you would normally use at Le Mans. And optimum grip is when the pressure is more like 1.8, 1.9 bar. So you can see there are some considerations into the structure of the tire and how you can sustain the loads. And the vertical loads can be really high at high speed with the downforce we have. Now, knowing that, we have evaluated the grip that we can obtain with such tire. And again, these are coming from some of it from my own experience of having worked in Formula One and LMP for 20 years. And some of it came from validation from people working on this sort of tires, okay? And it's extremely important to have a realistic level of grip for the model we use. If the grip is going, if the grip would be 5% higher than our model or lower, the lap time would change quite significantly at the Nürburgring. 5% grip change would be nearly between 5 and 10 seconds lap time change. So it's a very big, it's a significant number. So it's important to be in a realistic window, because I don't want to sell the project based on predictions that we cannot achieve. I really want to have realistic numbers here. So the grip level that we obtain, as you can see, this is lateral grip, this is longitudinal grip, and this is front and rear. The front grip is always a bit lower than the rear. I've already explained in the vehicle dynamics module that the front end tends to be, we want a bit less grip on the tire than the rear to give some stability and some understeer to the car. It would be extremely difficult to drive a car with the same grip front and rear or more grip at the front than the rear. And also what we are looking at here is the change of grip versus the vertical load on the tire. Again, an extremely important parameter for the dynamic simulation. It's what we call the load sensitivity. So effectively how much grip we are losing when we start pushing on the tire. That's important because when you develop aerodynamics and add downforce to the car, there is a point at which it's not just about adding downforce, because your grip level is reduced as well. So you want to understand how much downforce you need to add. When you add downforce, you also add drag, so that will slow down the car. When you add downforce, you will create more lateral forces in corners and go faster. But as I said, there is also a trade-off with you're not doubling the capacity in the corner by doubling the downforce, because the grip level is reduced. There is what we call saturation of the tire with vertical load. And there is a lateral model here and a longitudinal model. So we have slightly different grip level. These tires tend to produce more grip in the longitudinal axis than the lateral axis. You can see 1.85 longitudinally for 1.75 laterally. So it's about 5% stronger in the longitudinal direction. So we are in a really good place here where we have a model that is accurate enough in terms to give us a really good prediction on performance. And that's what we're using in our Unity simulation. The other parameters that matter are the speed radius inflation. So as the tire is going faster and faster, rotating faster and faster, it's growing by about 5 millimeters between 0 to maximum speeds. But obviously, we are also pushing down more and more on the tire, so the diameter will decrease because the tire is deflecting. All in all, that deflection is canceling more or less the inflation due to the centrifugal force. So these are important numbers to have. We also have stiffness numbers, in vertical stiffness, which, for your information, we are not using at the moment in Unity. In our dynamic simulation is currently is using a stiff tire. It's something that we are changing as we speak. Eddie is developing, he's been working on it for the last 4 or 5 months. It's a new tire model that will have deflection in all directions, multiple contact patch points. And I will show you actually a picture of it now, so you understand what I am discussing here. that's a good way for me to show you that you can access all of this on pairing.com. So there is a thread called Unity VPP development. This is where Eddie is working most of the time. In fact, you can see Eddie spending time and earning tokens as a result. And Eddie has put some images that I want to show you. So if you just need to load more messages. Okay, there you go. So Ed is working on this new tire model that will have, currently we have only one point of contact with the ground, and the tire is infinitely stiff. So all we have is a wheel that's like a solid body, and we're checking the contact with the ground in the middle of the tire. We are now moving to a much more sophisticated model where we'll have any number of points. This is 5 here, but we can have 9, 11, any number you want across the width of the tire. And we're going to check the penetration of each point on the road. And the contact patch is going to move. It's going to basically be the center of pressure based on all these points that we are calculating being in contact with the ground. So you can imagine it's a much better way to interact with the curbs, for example, on the side of the track. At the moment, this scenario where there is a curb and the tire is intersecting, we don't feel anything in 424 simulation right now because we're only looking at the middle of the tire. But very soon, and I believe it will take another few weeks, maybe less than a month before we have this model ready, we're going to start having effects from, the shoulder of the tire touching the curb. So it's going to be a much more realistic feel, and the tire will also deflect based on this stiffness that I talked about. The tire will deflect vertically, but it will also deflect laterally. So like the threads moving on the wheel, and it will deflect as well longitudinally. And that will again improve the sensation of driving and affect a little bit the performance and the setup for the car. Okay. That's a nice way to visualize what Eddie is doing. Here you've got an animation showing you where, as we turn the tire, these points are recalculated. And you can see the contact patch is moving because he's on an uneven ground. And when he's turning the wheel, the contact patch is moving to the shoulder of the tire. Contact patch is the center of this cross, of this coordinate system. For your information, and that shows you the level of the depth of development that we want to achieve. With Eddie, we've been working for 4 years now, and there was work to be done on the aerodynamics model to make it more, more advanced. A telemetry system that we've developed in Unity. We had so many features to develop, but we knew from 4 years or even 3 years ago, I think, is when we started talking about this, we needed a new tire model. It took us all this time to do the other features, and now Eddie had enough time to develop this new tire model, which is going to really be amazing for realism. That is also combined with a new suspension model. The current suspension model is a pure vertical model. We are going to a more kinematic model with a center of a roll center, anti-dive, anti-lift, which I'll explain in a minute when we talk about suspension. Here is another example of, you see each point contacting the ground has got a different penetration and also a normal. And based on all of this, Eddie is recalculating the contact patch center, and this is where the final load is applied. I want to come back a bit more in history. I like to show you what's happening in pairing.com because you can access all of this. I'm going to load some more Here you go. This is the development of the suspension model. And basically the suspension model, you see 4 wheels here, and all these lines are the lines of actions and the center of rotation of the suspension in space. So we are not anymore a pure vertical suspension movement. We have the true rotation of the wheel around the chassis. I'd like to show you another image that I'm thinking of, but I don't think it's... here you go. I just wanted to say, part of the development we are doing right now is working on this. So we have a center of rotation of the wheel. So when the wheel is going up and down, it's rotating, not only going purely vertical. And we have also this spring model with a stiffer part at the end for the bump rubbers. So it's just a better way to set up the suspension of the car. So that's coming on 424 in about 3 or 4 weeks. When it's coming on 424, we were going to do a lot of testing. Our driver's going to drive this. There's going to be setup changes to the car to adapt to these new models. But as you can see, we are not stopping development of the physics engine, we call it, the models that are underpinning the dynamic behavior of 424 in Unity. Okay. So this is it for tires at this stage. If you have any question on tires, please let me know now. No question on tires today? Okay. All clear. So let's move on to suspension. And here I'm just doing a quick summary of the main parameters for a suspension model, and then I'll show you the parameters that we are using for 424. So you all know about camber, which is obviously negative camber is what we're normally using statically, so that when we go in a corner, the tire is more or less vertical because of the role of the car. We have things like caster offset and caster angle. So that's especially important for the front because it affects the steering loads. So when you're cornering, it affects effectively the feeding back to the steering wheel for the driver. And from a front point of view, you've got what we call the kingpin angle. So it's this angle between the axis of rotation of the wheel, the steering axis of rotation, and the axis of the wheel, and then the scrub radius. Remember this, because in a minute I will explain something quite important for 424. The fact that we had to reduce the scrub radius and the kingpin angle because the car is 4-wheel drive, and we were having quite bad steering reaction initially when we were using the old kinematic model. And then the roll center of the suspension is the height of this point relative to the ground. Just think of it as the higher the roll center, the higher this point is. This point is the instantaneous center of rotation. So the wheel doesn't go up and down vertically. It actually rotates around a point, and this point is the roll center. So if the roll center was on the ground, it would rotate like this. If the roll center is very high, it rotates, but the wheel goes away from the chassis. And it's important because when you're in a corner, if the roll center is high, there is a lateral force that creates a moment around the center of rotation that lifts the car up. If the roll center is on the ground, the lateral force is in line with the roll center, and there is no rotation, or there is no movement of the chassis induced by the cornering. But in the case of 424 and Formula One in general, cars that are driven mainly by aerodynamic performance, we are not so sensitive to the height of the roll center. The decision is made in a different way. we decide on the roll center height in order to have the wishbones attached to the chassis at the points where it's the stiffer. And because the chassis is fairly high for aerodynamic reason, you find that when you attach your suspension, the roll center is fairly high. So some of these decisions are made based on aerodynamics more than purely the behavior of the suspension. So let's dive into some numbers here. So first of all, I'll open this kinematics document. And that's where I summarize the parameters for 424. This is the front table here, and this is the rear table. Each line is actually a different car. I've put some numbers coming from my experience and estimated for Formula One here, for LMP1 here. These are just reference points for me. And then 424, we've got 2 lines for front because we've been doing some changes. At the rear, there's this 1 line here. We are now on what we call the low KPI, kingpin inclination, kingpin angle or kingpin inclination. Remember this kingpin angle? We've had to move to a low KPI suspension. So effectively the caster angle, the main chain has been the kingpin angle. We used to have 12 degrees, it's gone to 2 degrees. So I'm talking about this angle here. And the reason we've done this, as I said, 424 is a 4-wheel drive car, but it's got a lot of power at the front. And when you put torque through the drive shaft at the front, there is an induced moment around the steering axis that the driver feels. And what used to happen is when we were on the standard suspension here, you would put your foot on the throttle for corner exit, and the steering wanting to open itself. You could feel torque against your steering angle. So imagine you put the throttle on and the steering was opening, pushing you outside of the corner. And that was coming from these parameters. So we've gone to 2 degrees, and that effect has reduced dramatically. And the other thing that we've done is reduce the caster angle a little bit. That also has decreased a little bit. That we call it torque steer, so or power steer. So when you put power on with the electric motors, it steers the car depending on if you're on under braking or on exit. Now, the reason why I wanted initially to put 12 degrees is when you have more angle, your suspension arms are more away from the wheel. So it's a bit easier to package and design the suspension points. When you go to 2 degrees, your suspension is more inside the wheel and your attachment points are more inside the wheel. So we had to change the design of the uprights. Let me show you what it looks like in CAD. Let's go here. You've seen that before. We can open the CAD in Onshape straight away. If I go into suspension here, kinematics, I'm on the front 424 here. Okay, so this is the wheel axis. This is the center of the wheel. And this is the axis of steering. And if I measure the angle between this and this, so it says 5 degrees because we're in 3 dimension. I have to do it in the 2 dimension space, 2 degrees. You see it here, 2 degrees, okay? So that 2 degrees is effectively this number. But with 2 degrees, as I said, these points where the wishbone attach on the upright are closer to the center of the wheel. So there's a bit less space, but we found ways to make it work. But basically, these points are moving inside the wheel more. I can show you other numbers. So we've got the roll center height at the front is 120 millimeters. If I go here, basically the center of rotation for the suspension is far away here. The line connecting back to the tire contact patch is here. And if I measure between the point on the center line of the car with the ground, 120 millimeters. That's the roll center height. So these sketches have been built using these parameters that I have summarized here. We can look at the kingpin offset as well. 35 millimeters should be the distance between this point and this point, 34.8. Okay, it's because I took the wrong point. It's this one versus this one, 35. So using all these, basically using this list of parameters, you are able to constrain these sketches. This is what I call the front view kinematic sketch. It's looking at the car from the front, and the side view is here. And the side view sketch is mainly constrained by the anti-lift and the anti-dive angles, 8 and 4 degrees, which corresponds to, I cannot go inside the sketch because I'm not logged in. So let me sign in now. Okay, great. I come back to that side sketch. And you can see the 7 degrees here. In fact, there is a discrepancy. Is it because I am looking at the rear? Sorry, I'm at the rear. So here I'm on the side sketch for the rear. 7 degrees is the 7 degrees anti-rise angle. I'm not going to go today too much into the details of what is anti-dive, anti-lift. It's obviously the effects of braking or accelerating on the chassis movements. But I just want to say again that the decision for these numbers, so if I go back to the front, the decision is mainly based on where do I want to attach my wishbone. Not only, some of them are purely for having a certain amount of anti-lift, anti-dive, and chassis movement, but you can see that the wishbones are fairly high. This is the line for the drive shaft, and the low wishbone is just under the drive shaft, and it attached at a height of 245 millimeters because the chassis is fairly high. Let's go into the final assembly, just so I can illustrate what I've just talked about. Here I'm gonna isolate the chassis. Okay, so if I can find it. Okay, main chassis is here. And the suspension. I will take all of the suspension. And I'm gonna isolate, oh, wrong button. I'll do it again. I'm gonna isolate this. Okay. So what I want to show here is, you see the low wishbone is attached more or less to the angle of the chassis. So what I've defined first is the best height for the chassis is fairly high. It cannot go higher than this because of the drive shaft and the motor, the electrical motor and the transmission. But it's as high as possible to leave space for the aerodynamic flow under it. Once the chassis height is defined, if the car was not four-wheel drive, the chassis would be higher because we wouldn't have the constraint of putting the electric transmission in. And Formula One chassis tend to be a bit higher. Once I know the height of my chassis with that corner, I basically attach the wishbone in where I can attach it. and I've got a similar, and that defines more or less the roll center height. This is why it's fairly high on the car. And then I have obviously the constraint of putting the top wishbone as high as possible, just to create some distance between my wishbones, just for stiffness. But as I explained before, as you can see, the wishbone's going fairly far into the wheel because of the kingpin angle is low. I'm showing you the wrong arm here. This is the wishbone here. Okay. So the top wishbone is going to attach about there. It's fairly deep into the wheel. And remember, you need to be able to steer. And when you're going to steer, the rim is going to get closer to the wishbone. So when we realized we have to reduce that torque steer I talked about because of the four-wheel drive, we reduced the kingpin angle. We put the wishbone more inside the wheel. That meant from the top view, we had to close a little bit the angle of the wishbone, just so that when we steer, the rim doesn't touch the wishbone. So you see, these decisions are made from aerodynamics, packaging space, where is my chassis, where can I attach my suspension? If we go to the back of the car, it's a different story. Let me show you the suspension with the casing. So at the back, the casing is where we have the transmission, and I'm gonna add the suspension to it. Isolate. Okay. At the back, we are attaching the suspension to that casing here. You can see from the top. First of all the wishbones are going forwards because I don't want the casing to be too big at the back for aerodynamic reason. Oh, I didn't want to do this. So for aerodynamic reason, the casing is fairly small at the back. You see how thin it goes? Because the diffuser is under, the top body is over it. So it's the size of it is just big enough so we can put the electric motor on the transmission. See, it's not very big. And it's centered around the drive shaft and the transmission, so it's aligned with the wheel center. Once I know that, I know where I can attach my suspension legs, so the wishbones from the lower and the top one. And that's what defines more or less my roll center, because once I have the wishbone location, I define the roll center height to get the wishbones in the position I want. And this is driven by aerodynamics as well. Because if I do a section of the car, let me see if I can do it. Let's do it like that. You see how the diffuser is just under the casing. And the top body as well is going very low. So we are being squeezed by the aerodynamic constraint. So it's an aerodynamic car, okay? We are really trying to squeeze everything inside the car, not too much, but enough so the aerodynamics is working as best as possible. So this is what at the rear, we have a roll center height of 75, so it's lower than the front. Now the camber gain is how much camber the wheel will take with vertical displacement. And this is based on, you can see it's based more or less on experience, because between Formula One and LMP1 cars, these numbers are fairly constant. And at the front, we're close to zero as well. This is based on how much suspension movement I will have, how much camber I want to correct in corners. The static camber is also fairly standard, so we use 2 degrees at the front and 1 degree at the rear. We have less camber at the rear. We want the tires to be more upright, vertical when we are accelerating in a straight line or exit of corners, because most of the power is at the back. Now, the last number I will talk about, we've got what we call design ride height. So we design everything for a ride height of 40 millimeters at the front, 60 millimeters at the back. And we have a ride height operating window of 10 to 70. So at the front, the suspension can move so that the chassis go as low as 10 millimeters from the ground and as high as 70. We are measuring this from the bottom of the floor. At the rear, when it's at its lowest point, we're 20 millimeters away from the ground, and 100 when it's at the highest point. As you can see, the rear, we have 80 millimeters travel, top to bottom. At the front, it's 60 millimeters. So the front is kept a bit more, it's a stiffer suspension and it's kept in a smaller window of movement because the aerodynamics is more sensitive to front ride heights. So we want to keep it to a smaller window. So if I come back to my section here, this is nice actually in Onshape. You can measure things in a section. So if I say, okay, I want to measure the distance between the ground and the floor, I can select a point here. It says 42 millimeters. It's not 40 because if you extend the floor to the front axle, it would be exactly 40 millimeters. But the floor doesn't extend to the front. But if I measure it at the rear, so I'm going to unselect the front points. But the rear, again, the flat floor doesn't extend to the back. But imagine if it was extending. But if I measure it from this point, we're at 55.8. So if you extend that line, that line, the flat floor, to the rear axis, you would be exactly 60 millimeters from the ground. So the ground line is here. The ground is designed because we want to understand where to design our suspension. So because I said the design ride height is 60 millimeters at the rear, and what I do is I take the tire diameter, the ground, and I put a 10 millimeter intersections because I consider that the tire is always deflected just under the static weight of the car. So effectively, that gives me an accurate position for the wheel. I always use about 10 millimeter. In fact, we can measure this. We can do a section. Well, if we move the section to be where the tire is, and if I measure between the ground and the tire diameter, but effectively it's not going to give me, it's going to say 0 because it tells me the minimum displacement, the minimum dimension between the two. So I can't, I'd have to select a point here, which I can't do. But anyway, this is 10 millimeters. And at the front, it's also 10 millimeters, okay? So this is how I design everything. Everything's constrained this way. If I come back here, I talked about the kinematics. One document I want to show you is quite interesting as well, and it's linked with the story about the torque steer. I've got this document called the Link Load Solver. This allows to quickly understand the load in each suspension leg based on the tire contact patch load. So what I do is I input the suspension kinematic points. So for each wishbone, track road, it's basically the sphericals or the point of kinematic movements around the front suspension. I do the same for the rear. And then there is a matrix calculation. And at the end, we get these coefficients here. This is the load factor for the front and the same for the rear. So what it tells you is for each leg, so the legs are track rod, push rod, wishbone lower forwards, lower rearwards, upper forward, upper rearwards. It gives you a factor. So imagine you want to know what is the push rod load, the compression, when I push on my tire vertically. So for 1 unit of vertical FZ, vertical load at the tire contact patch, I get 3.65 unit of compression in my push rod. That's fairly easy to understand because if I look at my suspension model, let's go back to the suspension kinematic model, or let's go to this assembly here. And we're going to do a section, so we only show the front. Okay. So effectively, the push rod is at the very top. I couldn't put the push rod lower than that because of the drive shaft. So it's a fairly unconventional way to put the push rod, but I believe one that will work well for us. So effectively, when we have a vertical load at the contact patch, because of the angle of the push rod, so when you push by 1 unit, it will create 3.65 times the load. That's why we've got very high load in the push rod. There's like a motion ratio effect. So 3.65 at the front, 3.04 at the rear. The push rod is slightly more vertical at the rear. And that's how we know. So I use these calculations to tell me what steering load I would get. So if you look at the track rod, so the track rod transfers the load from the suspension to the steering rack. And using these numbers, in Unity, we calculate dynamically the steering load from the track rods left and right using these load factors. So when you're braking, it creates a force in the X direction. When you're in corners, you've got a lateral force inboard, depending on the sign, and then the vertical load. You can see these load factors are fairly low. That's because we've gone to the low kipping angle suspension. We had to do this, especially for this one number here. The mx is the moment coming from the drive shaft that was inducing too much steering load. Okay, so using this little calculator, very useful, I was able to redesign the front suspension to reduce the torque steer. We've been testing this new front suspension with Augusto and Damien in the simulator. So we've done really a lot of engineering testing in Unity to come up with a front suspension that will be working well for the demand of the four-wheel drive system on 424. In fact, as an illustration, the front suspension you see here is the old model. You can see the top wishbone was attached fairly away from the center of the wheel. So if you draw a line between the top and the bottom points, that was the 12 degrees old suspension, and the new one is much more vertical. So that's for the link load solver document. I've put here for your information the damper spec for 424. These are basically the dampers we will use front and rear. And the way we define the damper is a damper is producing a load based on the speeds of deflection, compression, tension, or I should say the speed of the shaft going in and out of the damper. And typically the dampers will produce loads of about 2 kilonewtons for velocities of 300 millimeters per second. but it's not we are not using linear dampers. We have dampers that are a bit stiffer up to a point at low speeds, and then the damper has got what we call a blow-off or a valve system that changes the slope or the characteristic of the damping. So you've got a low-speed damping, high-speed damping. And the front typically has got a bit less high-speed damping than the rear. But these numbers will change when we test the car in real life. That's more or less based on experience. So that's there for you. There is also another document that was created here, and I can open it now. And that's a summary of the front and rear suspension. You've got all the kinematic points. Got some views here. Some of them are actually need updated because, as you can see, this is still the old front suspension on the images. The new front suspension has been kinematically designed, but still need to be detailed. So still some work to be done there. And the same for the rear. In the rear suspension model here, you can see the torsion bars. So the push rods activating the rocker and the torsion bars and the dampers. That will also change because I have moved the motors at the rear. So the rear suspension needs redesigning as well. Okay. Any question on suspension? Yes, Wojciech?
You said that the roll center of the suspension is important design parameter you start from, but not all suspension geometry leads to the constant point of rotation. Is it somehow required so it is constant, or just your decision?
No, it's actually not constant. You're absolutely right. Even with 424, it always changes. So what I've shown you here, when I say the roll center height is 120 millimeters, it's only true at the 40 millimeters ride height design.
Oh, I see.
Yeah. It's just like the way for me to constrain the suspension at one design position. We always do that in design because after that, you're right, there is more parameters, which is how does roll center vary when the suspension is moving up and down.
So it just says what is the curvature of the trajectory of the wheel at this single position.
Yes.
Okay.
But in fact, it's already defined because if you look at the kinematic model here, that's the front view. So the instant center of rotation is there. It's quite far away from the wheel. This is the center of the car. This is the center of the wheel. The reason it's so far away, it's mainly defined because of the camber gain. Because the camber gain is how much angle where the wheel is going to take when it goes up and down. If the camber gain was much higher, the center would move closer to the wheel so it could rotate more. Obviously, that point is defined by the intersection of the wishbones. When the suspension moves up, that intersection is going to move. It's going to probably move down a little bit. And also then that line will move and it will intersect the tire, and you can see the roll center is going to move as well. But this is a level of simulation that we are not necessarily taking into account too much in 424 at the moment. And to be honest, I do that because so in the Unity simulation, we are defining a constant center of rotation. So there is a degree of simplification there. In reality, that center is moving, but the impact on vehicle dynamics is very, very small. So it's a compromise between how much complexity we want in the model versus what we need for the behavior of the car to be realistic. In fact, at the moment, as I said, we don't even have a center of rotation. The tire in the Unity is moving up and down purely vertically. So it's like saying that the center of rotation is infinity on the left.
Mhm.
So I'm just going one step at a time in terms of making the models more complex. And some of it is not really going to affect the behavior of the car much. It's to do with the fact that 424 is an aerodynamic car, very stiff suspension, so the movements are very small. Okay.
Okay, thank you.
Any other question on the suspension? Okay. So let's finish with the brakes. And I wanted to talk to you about braking on 424, also because braking is also associated with the electric powertrain. So I explained before, but the way we brake with the car is about 70-80% done on friction brakes. So we call it friction brakes is traditional braking with the disc and the pads. And 20-30% is done on electric regen. And I will have to show you again this torque maps document, because it starts from here. What we are defining is when the driver is pressing the brake pedal. So you need to look at these plots, and all the negative numbers are braking negative torque. When the driver presses the brake pedal, we are doing electric regen and we are doing friction brakes. And the gains we are using, or the relationship between brake pressure and regen, is 33 Newton meter per percent. What we call 1% is in Unity is 1% of maximum braking. So when we are fully on the brakes, it's 100%. And we are asking the car to produce 33 Newton meter per percent of braking from the electric motors. And on the friction brake, we're asking 100 Newton meters per percent. So effectively, when I brake, I have 100 Newton meters from the friction and 33 from the regen. So if you add the two, it's 133 Newton meters per percent of brake. If I brake at 100%, it's 133 times 100. So it's 13,000 Newton meters for the whole car. And the way we split front and rear, when it comes to friction braking, we are using a constant hydraulic, well, we call it, it's the old way of talking, hydraulic brake balance of 65% at the front. And for the rear, it's variable. It starts, so it's this blue line here. It starts at 70%, which is the maximum. At maximum braking, we are putting 70% of regen at the front. But as I release the brakes, it goes backwards, and we're ending up at 15% at the front and 85 at the rear. That's how we achieve a variable brake balance. The friction brake balance is constant 65, but the regen balance is variable. So when you're pressing the brakes fully, your brake balance, or what we call torque balance at the end, when you add the friction and the regen, it's going to be a combination of 65% and 70%. In fact, we can see that number here. If I show you the line at 100% braking, we're at 66%, depending on the velocity of the motors. We are about 66% of torque balance front and 34 rear. As I release the brakes, imagine now I'm at 30% brakes. my torque balance is 52 at the front, 48 at the rear. If I release even more the brakes, I'm starting to be at 49 front, 51 rear. There is a point where the braking is big, we are braking more with the rear than the front. But this is only when you are very, very light on brakes. This is when you are entering the corner. And I explained to you before that we are doing this to avoid locking the front wheel and to help the car rotating. So this document is really important because it's going to be exactly the same formulas we will use with the real 4x4 car. It's driven by software. It's taking the pressure that the driver applies on the brakes, which is still connected to the hydraulics friction brakes. We are measuring the pressure inside the master cylinder, and we're calculating the motor torque based on that pressure. And obviously that pressure is also creating the friction brakes with the traditional friction system and the calipers. Okay? So we are achieving, it's a very simple system to achieve variable brake balance using the regen and the friction brakes. We have, as you can see on this plot, the lines are not all horizontals. We have some limits that are coming from, you see here, the motors are limited by the maximum power that they can generate. So when you're at high speed, so this axis here is rotational speed of the wheels or the final drive. So effectively, the motor is a single speed gearbox. So we don't have gear shifts. It means if you look at the speed of the motor, it's like looking at the speed of the final drive or the differential. The maximum velocity, rotational speed of the final drive is about 2,700. Wait, it's that number here. 2,800 revolution per minute. When you're rotating so fast, your torque is limited by the power curve. You can see this. You see this curve here is limiting how much torque can be produced because the battery just is limited in power at that point. So even though we would want to achieve more torque from the motors and keep these lines horizontal, we are limited by the power, which is why on the total torque here, you can see the lines are horizontal at medium brake pressure. At maximum brake pressure on high speeds, the friction brakes are still working as they should, but the motors are limited by the power curve. But the limitation is fairly small when you look at it on this graph. It still has a little impact on linearity of the system. So what the driver will feel is that he would expect maybe a linear torque versus how much he pushes on the brake, but there is saturation coming from the electric motors, and you can see it here. But that saturation is very short-lived in time because as soon as you release the brakes, you're into the linear region of the motors, and you're not power limited anymore. The rear power limitation doesn't really come in because you're at high brake pressure, you're mainly asking the front motors to regen, not so much the rear. As I said, the rear is mainly used at lower brake pressure, but at this point, the amount of torque needed is low. So I hope you understand using just these graphs where we've got all these calculations and we take into account power limitation, torque limitation of the motors, and we can very quickly change how the brake behaves for the driver. Okay? But obviously, we are still using friction brakes on the car. So we've got a little presentation here. And this is just showing you how we've been defining the brakes we want to use. So we started from using the Unity simulation, and that gave us the amount of torque we need from the friction brakes. This is summarized here on this plot. So this is Nürburgring lap, and every spike is a braking event. And I had to, when I went to select the brakes for the car, I had to give to the manufacturer, which is Brembo in this case. They're basically manufacturing carbon brakes for LMP cars for Le Mans, so we are using these products. We need to check what is the maximum torque in Newton meters that we want from a single wheel. And this will be at the front where the maximum torque will be. You can see here values of about 4,000 Newton meters at high brake pressure. And this was slightly too high initially, so this was done in 2021. We did another version in 2022 just by adjusting some parameters and just to reduce that peak torque on the disc, because the discs are structurally, they are dimensioned for maximum torque. So this is how you select your this is, by the way, just a single point at maximum brake pressure, looking at a certain speeds. It's got a car mass, a drag level. That allows us to very quickly model what torque level we're going to have on the brakes. And then we go to the Unity simulation to get the full lap picture. Based on that, we selected some brakes from Brembo, which are standard braking system for Le Mans hypercars. Typically, we are using brakes of 776 or 780 millimeters diameter at the front. The rear brakes are smaller, 350 millimeters. Here is basically a mass model, summary of the mass. So the braking system at the front weighs 12.6 kilos, and at the rear, 11.3. That's a view of the system that we are using. The caliper here, it's a 6-piston caliper, and the carbon brakes. One thing that we're going to do for the Nürburgring is, you see the disc is fairly thick. The reason for that is because these are designed for Le Mans 24 hours. But for the Nürburgring, we don't really need that thickness because the wear is going to be very small. But we want a system that is as light as possible. So we are going to reduce the thickness of the disc and the thickness of the pads. So imagine we're going to get new disc and pads, and we're going to basically reduce their we are going to machine them away to be their minimum thickness. So when we go to the Nürburgring lap record, we are going to save about 1 kilo or 1.5 kilos for the whole car by doing this. What it will do as well is it will make the warm-up a bit faster. So the warm-up is when the brakes are cold, for the first 2 or 3 corners, you're going to warm them up each time you apply the brake pressure on. And as you know, we only do 1 lap, so we don't have much time to warm up the brakes. By using a thinner disc and pads, there is less thermal inertia, and we're going to warm up the brakes a bit faster. I can show you quickly what it looks like. If you go back to the CAD's model, in this open source CAD model, we are not allowed to share the exact CAD of the brake system. So I've done a simplified version, which you can basically see when you go into suspension. If I do a section of this model here, and I'm gonna rotate it so we see also the pads. We don't have this is the caliper. Okay, never mind. What I want to show you here is we have we've simplified the disk model and the caliper just so we can open source it in this model. And this is the model used for CFD as well. We don't need the accurate model for CFD. But you can see here, basically this thickness, you see this separated parts. This is the amount of brake disc that we're going to machine out. So the disc we're going to use for the Nürburgring is going to be this one. It's going to be thinner than the actual new disc. This is normally the wear that you get during more than a Le Mans race. If you do a full Le Mans race, you're going to wear the disc by maybe 2/3 of that amount. but Brembo allows the disc to be a bit thinner. So we're going to go to the minimum thickness allowed. Okay, so that's what I wanted to talk to you about today, about the brakes. And if you have any question, let me know now. So I've got 2 hands raised, but I imagine these are from before, unless you have a new question. Okay. So Wojciech again, yes, please.
Yes, I have new question. Uh, you said that by controlling with software the amount of region braking, you effectively maintain some desired braking bias, right? Braking balance.
Correct.
So do you take into account the variable temperature of braking discs to maintain this balance?
So no, the answer to that is no, we don't. At the moment, we consider the friction brake to be always, we don't have a thermal model. We don't have the temperature coming in play. So the reason for that is in the operating window of the brakes are fairly consistent as long as you're using them between a temperature of 200 degrees up to 800 degrees. There is a small variability, but we checked that with Brembo, and the way it works is the rear and the front and rear brakes are going up in temperature together and cooling down together. So the relative change of friction coefficient front to rear stays the same.
So the balance won't be affected even if the actual friction is different.
Correct. Yes. There is small variability. It might be 1, 2, or 3%, but we haven't got that in the model, to be honest. And yes, maybe it's something we need to model in the future. It's always very difficult to model these things because if you do a thermal model and you have very quick variability of temperature on the brakes, then you might take some setup decisions as a result. But when you go in reality, this temperature will vary in a slightly different way. So I prefer to stay what I call like cold model. So we don't have variability with temperatures. We do the same for tires. The tire is a cold model. We don't have temperature variability. When we go to the real car, we're going to see variability in temperatures, and we're going to try and manage that the best we can on the real car by adjusting the setup a little bit.
But we will have the sensors to measure the temperature on board.
We're going to have sensors to measure the temperature. We are, to be honest, we are very lucky that nowadays the products that we're using are very consistent with temperature. I remember 15 years ago, 20 years ago, when I started my career, the brakes were more sensitive to temperature than they are now because they've done improvements in consistency with temperature. Because the drivers have complained, they said, the brakes that have no grip or no friction when they're cold, and then suddenly they're biting, they're saying then starting to bite, and it's not good for the driver. He wants some consistency under the pedal. So the manufacturers of brakes and tires, the same with tires, it's true, especially at Le Mans. Michelin has got a very, very good product when it comes to consistency with temperature. It's a bit less the case in Formula One, where the window is a bit smaller, the operating window. But at Le Mans, because they need a tire that is more consistent with different conditions of track, temperature, they have a wider operating window. And that's the sort of product we're going to use.
Is there a way to directly measure braking torque? So it is easier to control it?
So you would have to, it's extremely difficult, to be honest. You can. What you do is you need to equip your suspension legs with strain gauge.
Mhm.
So you measure the loads on all the suspension legs. This way you come back using the table the link solver, that I explained, presented today. You can then reverse engineering the loads on your contact patch, and therefore the torque applied by the brakes.
What about some gauge between the braking disc and its attachment? So
So I've never seen this done before. In theory, it would be possible. Yeah, maybe on the what we call the disk bell, which is the attachment of the disk on the axle. I haven't done it myself. I haven't seen that before, but maybe it's possible. What we do typically is we go on a dyno, so not on the car. We go on a dyno, and basically Brembo will measure the brake torque at different temperature and different pressure in the caliper, and they will give you that information. So you're going to have maps of friction. They will give you a resulting friction coefficient on your between the pad and the disc.
Okay, thank you.
Okay. Any other question on the brakes today? Okay. Well, if there is no more question, I think we can stop it here. But thank you so much for attending the session today. And there will be a next session next week. So I'll see you there.
Thank you very much.
Thanks, everyone.
Bye.
Thank you.
Thank you.
Thank you.
Bye-bye.
Thank you, Nico.
Thank you. Bye.